So the next concept we got to hit up is what we call stereochemistry. And stereochemistry is really simply defined as just what do these molecules look like in 3 dimensions. If you've noticed, we've been drawing our diagrams so far on just a 2-dimensional board or a piece of paper. And so the fact of the matter is we don't live in a 2-dimensional world, we live in a 3-dimensional world. And so because of that, these molecules have 3D space that they can operate in. And because these bonds are made out of electrons, and these electrons don't like to be close to each other, they have 3D space to sort of orient themselves. And so what we use is something called VSEPR Theory to describe what these 3D shapes are going to be. And VSEPR is just an acronym here, and I've written out on the side, Valence Shell Electron Pair Repulsion Theory. And all it really means is this, is that we have these electron pairs and they repel each other. And so as we kind of go through this concept of electron pair repulsion and understand the fact that, hey, these electrons don't like to be close to these electrons if they can help it, will help us understand these shapes a little bit better and why they form these particular shapes the way that they do. Now there's 5 shapes that you need to be aware of. I've listed them here. We're going to go through an example of each one, show you how you can draw them, how we can determine what shape certain molecules are going to be, and give you the information that you need to know in order to be able to do these. So I'll be right back with our first example, so stick with me. So first up is the linear shape. The first thing that you need to identify when you are doing VSEPR diagrams is you have to ask yourself 2 questions. How many lone pairs are on the central atom? And how many bonding groups are on the central atom? So we've established what a lone pair is. We know what lone pairs are. It's just a pair of electrons that's not involved in bonding. So it's not attached to anything. But a bonding group is kind of a new concept. What a bonding group is it's just a group of electrons in between 2 atoms. Now, if I kind of give you the analogy of if I've got a group of 2 people or a group of 10 people, yes, the groups have different numbers of people in them, but they're both still considered one group. This is a group of 2 and this is a group of 10. So it's the same for groups of electrons when we're talking about bonding groups and VSEPR diagrams. If I have a group of electrons and there's only 2 of them in there, then that's still considered one group. If I have a group of 4 electrons, that's still considered one group. If I have a group of 6 electrons, still considered one group. So you can see in this example here that we did before, we did carbon dioxide, and here's the Lewis diagram that we illustrated in the previous video, and then the structural diagram that we also illustrated. The reason that drawing Lewis diagrams is important is because we need to have the Lewis diagrams in order to be able to determine what the structural diagram is. And in order to determine the VSEPR diagram, we need to know what the structural diagram is. So here I look at my structural diagram and I say, okay, right here I have one group of bonds. So this is one bonding group, and this is a second bonding group. And so for carbon dioxide, carbon has 0 lone pairs on it and 2 bonding groups, 1, 2. Yes, there's 4 sticks, but again, remember, we're just talking about groups of electrons. And so this is one group and this is a second group there. When we are determining the shape, again, also remember that this is only for central atoms. So I'm only looking at lone pairs on the central atom. I'm not looking at lone pairs on peripheral atoms. Those don't matter, okay? So how many lone pairs on the central atom and how many bonding groups on the central atom? Now, for a linear shape, this is the configuration. Anytime you have a central atom that has 0 lone pairs and 2 bonding groups, then you just simply say, okay, hey, I know that that is a linear shape. So that's how we know that this diagram is just going to be linear, which is just straight. So actually the VSEPR diagram you can see looks exactly the same as the structural diagram. And if I were to kind of use the model kits here to illustrate this to you as well, I've got carbon dioxide here as put together from our model kits, and you can see that this is just linear. It's just straight across. There's no bend or any sort of weird shape to this. It's just straight across. Now the reason it does this is because these electrons here, if you remember, VSEPR means electron pair repulsion. These electrons in this group want to be the maximum distance that they can be away from this group, because they're both negatively charged, and so they want to repel each other. And so the maximum distance that they can be away from each other is 180 degrees. If they bend any more this way, then they're going to start to get closer to each other down at the bottom. And so they don't want that, and so that's why they kind of generate this linear shape based on this. So here's the key right here. How many lone pairs, how many bonding groups does the central atom have? Once you can determine that it's got 0 lone pairs and 2 bonding groups, you know that that is a linear shape. Now, another linear shape that sometimes kids get lost in the shuffle with this is that if I just have 2 atoms that are attached to each other, it doesn't really follow this rule here of 0 lone pairs and 2 bonding groups, because A, there's no central atom here. You can see there's nothing in the middle. It's just 2 things on the outside. But because they're just connected by one set of electrons here, then it has to be straight or linear, just like this one. So compounds like H2 or HCl or HF, these are all compounds that are going to have a linear shape as well. It won't follow this rule, but there you go, you've got that. Bent or V-shaped is up next. So the same rules apply here, guys, where we need to identify how many lone pairs and how many bonding groups is on the central atom. So my example here that I want to go through with you is water. So if you take a look at the Lewis diagram of water, here it is. We turn that into a structural diagram, and here is where I'm going to look for my central atom and how many lone pairs and how many bonding groups it has. So here's my central atom, the oxygen. It has 1, 2 lone pairs and 1, 2 bonding groups. And this is the configuration that tells us, hey, this molecule is bent or V-shaped, when the central atom has 2 lone pairs and 2 bonding groups. So the way that I draw a bent or V-shaped molecule is just like this on the board. And you can see from this molecule right here that I've built from the molecule kit, you can see that on the top I've got these 2 holes, and that represents the 2 lone pairs that exist on the central atom, and then I've got the 2 hydrogens that come off. Now, because these bonds are made out of electrons and these lone pairs are made out of electrons, these guys are going to repel each other. And so this is the configuration that they repel each other to, is where these hydrogens are coming down and then these electrons are kind of on the top half of the oxygen atom. And that's what it looks like. I can draw this in the plane of the page. I don't have any atoms that are sort of coming out or into the plane of the page, and so 3-dimensionally, this is what this looks like. It's a very flat type of style of molecule with 2 molecules coming down. You can draw it this way, and this is why we call it V-shaped as well. And the name is good. You can either say this is a bent shape, like this, or you can say it's a V-shaped, like this, and you can draw it either way, it's fine. Trigonal planar's up next. Here's the configuration for it. The central atom is going to have 0 lone pairs and 3 bonding groups around it, and that's around just the central atom, remember. So here's an example of the carbonate ion, CO3 2-. Here's the Lewis diagram for this. Remember the square brackets with the charge on the outside. You can see that this carbon has a double bond here and then a single bond and a single bond on the other sides of it. And so again, here's the structural diagram. You can see that there's no lone pairs on the central atom, and there are 1, 2, 3 bonding groups around the central atom. So the structure for that, and again, model done here from the model kit, as you can see that I've got 3 oxygen atoms, and you can see that they've spaced themselves at the maximum distance that they can. There's no 2 oxygen atoms here that are any closer to each other than the other. It's an equal distance all the way around. And again, also a very flat molecule where I don't have any molecules coming out or into the page, the 2-dimension page. And so drawing these is quite simple, where we take the carbon and we just draw the 1 that's coming up and the 2 that come down in sort of a bent fashion, just like that. So that's how you draw a trigonal planar. So trigonal pyramidal is the 4th shape, and the configuration for this is that the central atom needs to have 1 lone pair on it and 3 bonding groups on it. And so an example of this would be ammonia. You can see the Lewis diagram here for ammonia, and then the structural diagram. Here on the structural diagram, you can see nitrogen is my central atom. It's got 1 lone pair and then 1, 2, 3 bonding groups. So that fits this description. So how do I draw a trigonal pyramidal shape. The thing that you have to realize about this is that now we're kind of getting into shapes where where these atoms are going to start to kind of come in and out of the page a little bit. So we have to be able to draw that so that we can depict what that really looks like. And so the way that the chemistry community has decided this is going to be drawn is that any atoms that are coming out of the page get drawn with this little wedge here, sort of depicting that this hydrogen is kind of coming out of the page a little bit. And any atoms that are going behind the page or into the page are drawn with these little dashes that kind of represent that. And then again, any atoms that are within the plane of the page, so right on the plane of the page, then we just draw the stick like normal, like we've been doing. And so you can see this one here, again, the electrons are the maximum distance away from each other, whether they're in a bond or whether they're a lone pair on the top. And so how I orient this, you can see that it's basically the same molecule no matter which direction I hold it. But if I'm looking at this with this diagram here, you can see that this hydrogen here is coming down. It's in the plane of the page, but this hydrogen here is coming out of the page, and this hydrogen is going into the page or behind it. And so we have to represent it like that in that diagram. So it's a little tricky. Give it some practice, try a few, and see if you can draw them. And that's trigonal pyramidal. Got one left. Okay, so the final and fifth shape here that you need to know for VSEPR theory is what we call a tetrahedral. And so the lineup here for tetrahedral is that we have to have a central atom that has 0 lone pairs and 4 bonding groups. So a really good example of this is methane, CH4. You can see the Lewis diagram. It was an example we drew before, as well as the structural diagram. You can see it, the central atom doesn't have any lone pairs on it, but it does have 4 groups of electrons. In this case, they're all individual or single bonds, but it does have 4 bonding groups, so that means it's a tetrahedral. Now, if you take a look at this diagram here, or this model, you can see no matter which way I hold this molecule, it looks exactly the same. And the reason the reason it's like that is because all of these groups of electrons are the maximum distance away from each other. And so the way that we see that this shape is now how we have to draw it on the page, which is, again, kind of like the previous example, trigonal pyramidal, is a little tricky because we do have a couple here that are coming in and out of the page. So again, you can see this one comes out of the page, so I use the wedge. This one goes into or behind the page, so I use the dotted lines for that. And so if my hand is the page like this, you can see that this hydrogen is in the plane of the page, this carbon is in the plane of the page, and this hydrogen is all in the plane of the page. They're not coming out or in. But this one and this one do. This one comes out of the page, this one goes into or behind the page, and so I have to draw those 2 atoms as such to represent that. And so this is how we draw a tetrahedral molecule. And you can just do some practice with those in the practice booklet, and the more practice you do with it, the better you'll get. So the last concept that I want to cover with you guys is a question that I often get from kids, and it's something that you do need to know, and we need to cover it. And it's this question of molecules that have multiple central atoms. So in a case like methanol here, I can draw this molecule using my Lewis diagram rules. And so I've got 14 valence electrons. You can see that I've got the carbon here, and I can stick these hydrogens around like that. But this hydrogen here cannot go here, because if I do that, then I've got to stick the oxygen around one of those hydrogens, because I can't attach it to the carbon. The carbon's already got a full octet. And so what I need to do instead is switch those around so that I've got something like that. And then I can count this up. I've used 8 plus 2 is 10. I have 4 left over. And so I'm going to place the leftover electrons around the peripheral atoms first. You can see the peripheral atoms already have a full octet, so now the central atoms is up. Carbon is also full, so the only option here is the other central atom, which is oxygen. And you can see that oxygen does fit the description of a central atom because it does have things around it. It's got this carbon and this hydrogen. It's in the center of some things. And so there are 2 central atoms in this molecule. Now, that diagram is finished. I'm at 0, all my octets are full. So if I draw my structural diagram for this, my structural diagram looks like that. Now, something I want to point out to you is that you can see oftentimes kids will ask me too, how come when we write chemical formulas, sometimes we don't stick all the atoms together? Like in this one, why is it not written CH4O? And the reason why is simply for us to have a hint on what the molecule really looks like in terms of its diagram and how it's sort of oriented. And so you can see here that I've got a CH3 group here, and then I have an OH group right here. And so that's why we write methanol like that as CH3OH, is to just remind us that, hey, it's got an OH group over here on the end, and something that affects how the molecule behaves, but also lets us know what the molecule looks like in 3 dimensions or just on paper when we draw the diagram. So here's the structural diagram for this. Now I can draw my VSEPR diagram. Well, how do I draw the VSEPR diagram with 2 central atoms? Well, what you need to identify is just what shape each central atom has. So if I kind of identify this as my first central atom and that one as my second, then this central atom here has 0 lone pairs and 4 bonding groups. That means it's a tetrahedral. So I'm just going to go ahead and draw that as a tetrahedral. So here's my carbon. I know I've got the wedge like this with the H and the H and the H there like this, and then the fourth one is the oxygen coming off right there. So there's my tetrahedral. Now I come back to this diagram and I say, okay, now what's the shape around the oxygen atom? Well, the shape is it's got 2 lone pairs and 2 bonding groups. That fits the shape of linear. That fits the description of a bent or a V-shaped diagram. And so I'm just going to draw this as a bent or a V-shape. So this is already coming down, which means this side then has to come up. And that's got the hydrogen attached to it there, which means I can just stick my lone pairs on the bottom like that. And so that's how I would draw sort of 2 VSEPR diagrams together that is in one sort of larger molecule. And there's lots of examples that you can go through in the practice that I've given to you guys. So go ahead and give that a whirl. And that's it for VSEPR theory. Thanks guys for watching.